So on the third day of this DC circuits chapter, what we're going to do is we're going to look at circuits that have multiple capacitors in them as well as batteries and do calculations of what's the equivalent capacitance and what's the charge and voltage on each capacitor, similar to what we did for resistors. Again, there's a worksheet or handouts available on Canvas for download if you want to follow along and save yourself having to draw a bunch of circuits. So capacitors that are hooked up in parallel, well, if they're hooked up in parallel, the ends are connected just with wire, same as we said for resistors that are hooked up in parallel. There's only wire between any of the ends. And that means that the voltage on each one is the same. So the voltage on each of those capacitors, C1, C2, and C3 is the same. But the charges are different because remember our equation for a capacitor was Q equals C times V. So Q1 is equal to C1 times V, Q2 is equal to C2 times V, and Q3 is equal to C3 times V. So if we hook those capacitors up to a battery, what's going to happen is a total amount of charge Q is going to flow out of the battery and it's going to get split up, part of it on capacitor 1, part of it on capacitor 2, and part of it on capacitor 3. So what we know is that the total charge that flows out of the battery is going to be equal to Q1 plus Q2 plus Q3. So if I draw an equivalent circuit, just like we did for resistors, where we have one battery and one equivalent capacitor, that equivalent capacitor is going to have a charge on it equal to the total charge flowing through the battery. So that's going to be equal to Q1 plus Q2 plus Q3. And Q equivalent is going to be C equivalent times V. So if I go ahead and I substitute in for each of those Q's, I substitute in C1V, C2V, C3V, then C equivalent times V is equal to C1 plus C2 plus C3 times V, and I can cancel out the V's because it's the same, and so the equivalent capacitance for capacitors in parallel is just the sum of the individual capacitances. If we hook up capacitors in series, now what happens is, remember that gap in between the two plates of the capacitor, that's an air gap and you can't actually have any charge go across there. So what happens is if I have a charge Q that flows from the battery from the positive terminal and a minus Q from the negative terminal, let's say, then they get stopped at the first capacitor that they encounter. So I actually have a charge of plus Q on the first plate of capacitor 1 and minus Q on the second plate of capacitor 3, and in between no charges can actually flow. So if I look at the region in between capacitor 1 and capacitor 2, you see there I've got minus Q plus Q. That's actually a charge of 0, right? And the same thing in the gap between C2 and C3. So no charge actually gets in there. Okay, so when the capacitors are in series, they all have the same charge on them, Q, but they have a different V because, again, remember Q equals C times V. So V is equal to Q over C. So we know the Q's are the same, and so the voltage on each capacitor is equal to that charge Q divided by whatever the value of its capacitance is. So if I'm going to replace that again with a single capacitor and a single battery, Q over C equivalent has to be equal to Q over C1 plus Q over C2 plus Q over C3. I can cancel out the Q's, and so I get that the equivalent capacitance, 1 over the equivalent capacitance, is the sum of the inverses, or C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3, and then take the inverse. So it's important for us to realize that capacitors and resistors don't behave the same when they're in circuit. So resistors in series, remember I is the same and V is different. And if they're in parallel, V is the same, but I is different. When we add up the equivalent resistance for resistors in series, we just add directly. For however many resistors there are. And for resistors in parallel, we add up the inverses. What happens for capacitors? Well, capacitors in series, we said Q was the same and V was different. And capacitors in parallel, Q was different and V was the same. So if you look at this, you can see, okay, well, whenever you have two things hooked up in parallel, V is the same, whether it's a resistor or a capacitor or a battery. Whenever you have two things hooked up in series, the voltages are different. So if you can remember what happens with the voltages, then you know what happens with the current or what happens with the charge. So when the voltage is the same, the current is different or the charge is different. When the voltages are different, the charge is the same or the current is the same. Okay, so last thing is, how do we add up capacitances? Well, for capacitors in series, we add the inverses and for capacitors in parallel, we add directly. So it's important to try to memorize this table. Make sure you know exactly how this works, because this is important for both concepts and for calculations for this chapter. So you really need to know all the points on this table for the test. Okay, so let's do an example. So what's the equivalent capacitance for this circuit? So here I've got three capacitors. C1, the one over here, is 10 microfarads. C2 is 5 microfarads. And C3 is 3 microfarads. So what's the equivalent capacitance? Well, we do the same thing that we did for resistors. We look at the circuit, see if there's something that's obviously in series or obviously in parallel, do the combination, redraw the circuit, and keep going till I simplify it to one single capacitor. So here, if I look, C2 and C1, those are not in series because, again, there's a place where the current, the charge can split off. But C2 and C3, those guys are obviously in parallel. Okay, so C2 and C3 are in parallel. For capacitors in parallel, we just add directly. So C23 is going to be 3 plus 5 microfarads or 8 microfarads. You notice here, because they're both in microfarads, I don't have to bother doing 3 times 10 to the minus 6 plus 5 times 10 to the minus 6. As long as I'm careful, I remember to put that my units are micro. So I'm going to redraw my circuit now. Where I had those two, I'm going to replace it with a single capacitor, C23. And now I look, what's the relationship between C23 and C1? Well, those are obviously in series. So if they're in series, I'm going to add the inverses. So C123 is going to be 1 over 10 plus 1 over 8. So remember, C23 was 8 and C1 was 10. And take the inverse, so I get 40 over 9 or 4.44 microfarads. So my equivalent circuit is a single 4.44 microfarad capacitor. And you should know, whenever you combine inverses, the result that you get should be smaller than either of the two things you combine. So here I combined an 8 and a 10, and I got 4.44. All right, so now we want to work backwards. This is what we had initially. We had, sorry, this is our final position where we have a 12-volt battery and an equivalent capacitance of 4.44 microfarads. What's the charge on that equivalent capacitor? Well, Q equals C times V, so I just multiply them. So 4.44. Now I have to do the times 10 to the minus 6 times 12 volts. So I get 53 times 10 to the minus 6 coulombs, or 53 microcoulombs of charge on that capacitor. Next thing I do is I step back one circuit in complexity, so I go to there. So these two capacitors are in series. If they're in series, they have the same charge on each other. So the charge on 1 and the charge on 2, 3 are equal to each other. and they're just equal to whatever the charge was on that equivalent capacitor up there, or 53 microcoulombs. So I can now figure out what's the voltage on each one. Again, use Q equals CV and rearrange it to get the V. So V1 is Q1 over C1, V23 is Q23 over C23. So 53 times 10 to the minus 6 over 10 times 10 to the minus 6. So I get 5.3 volts on C1 and 6.6 volts on C23. This actually, I think, was rounded, so it should have been 6.67, so 6.6 repeating and 5.33. And if I add those two up, I get that plus that equals 12. Okay, so there's a rounding error. If I add that, I actually get 11.9 because this should have been 5.33 and 6.67. All right, so now I'm almost there. I need to go back to my most complex one. So I know my V and my Q and my C for 1. I know my V for C2 and C3. It's 6.6 or 6.67 actually volts. And so now to find the charge on each of those, I just do Q equals CV again. And so I get 33 microcoulombs and 20 microcoulombs. And what do you know, if I add up those two, I get 53 microcoulombs, which is the charge that we said was on each one. So you can do some double checking just to make sure that your calculations worked as you went through. Okay, so let's do one more calculation. Here's an example with 6 capacitors, and I'm going to go over to my whiteboard to do that so I got a little bit more room. So here we've got 6 capacitors. C1 and C6 are the same as each other. They're 3 microfarads. C3 and C5 are the same as each other. They're 5 microfarads, and C2 and C4 are 2 microfarads. So I want to calculate what's the equivalent capacitance. So I'm going to simplify this down to one single capacitor. So let's look for something that's obvious. So what's obvious about any of these things? Well, if I look, C3 and C5, those guys are in series, right? There's nothing, no place in between C3 and C5 where any current can flow anywhere else. So C3 and C5 are in series, and if capacitors in series, we add the inverses. So C3,5, we'll call it, to let me know I'm combining 3 and 5. And let's see, C3 and C5 are both 4 microfarads. So 1 over 4 plus 1 over 4 to the minus 1. So that's 2 over 4 to the minus 1. So 4 over 2, which is 2 microfarads. So I can redraw that circuit. I'm going to redraw it. I'm going to replace that C3 and C5 with a single C3,5. So let me redraw it. Let me go over here. Let me see what I got. So I got a battery. I got C6. I go up. I got C4. Okay. Then I'm going to go across. I'm going to replace C3 and C5 with my C3,5 and C2, and then down here I have C1. Okay, so there's my redrawn circuit. So you'll notice that I did something here. I took that C2 that was up on the top and I slid it along. So whenever you're analyzing circuits, you can treat the resistors sort of like they're beads on the wire. So if I look at that C2, it can't go past any place where wires cross each other. So it can't go past those intersections, but I can slide it like a bead on a wire anywhere I want. And when I slide it and I put it in that position, it's quite obvious that these guys there, those guys are all in parallel. So C4, let's see, C2, C3,5, and C4 are in parallel. So what do? We just add them directly. So let's call the C2, 3, 4, 5 is going to be C2 is 2, C3, 5 was 2, and C4 is 2. So that's going to be 6 microfarads. Okay. While I'm here, I'm also going to look at C1 and C6. So C1, again, see there's these two places where that capacitor can't move past, but I can slide it like a bead on a wire anywhere. So if I slide it up to here, you can see quite obviously that C1 is in parallel with C6. And so we've got C16 is going to be equal to 3 plus 3, just adding directly, which is also going to be 6 microfarads. So now I've simplified myself down to 2 capacitors. So I've got two capacitors like that, C2, 3, 4, 5, and C16, and each of them is 6 microfarads. Okay, so we're almost there. Now we want to find what's the combination of those two. Well, those two are obviously in series, so I'm going to add the inverses. So C1, 2, 3, 4, 5, 6, or I could just call that C equivalent because it's my final one, is going to be 1 over 6 plus 1 over 6. And remember, we've got to take the inverse, and we get 3 microfarads. So the equivalent capacitance for that circuit is 3 microfarads. And then we could work back and we could find what's the charge on each one. So let me draw my final circuit. So here I've got 3 microfarads, and I've got, what's my voltage? 12 volts. Okay, so 12 volts, 3 microfarads. What's the charge? Q equals CV. So it's going to be 3 times 12, or 36 microcoulombs. Okay, then I can take that up here to this one and say, okay, so there's 36 microcoulombs on C2345 and 36 on C16. So the voltage on C2345 is going to be Q over C, 36 over 6, or 6 volts. And V16 is going to be 36 over 6, which is 6 volts. So since I had microfarads and microcoulombs, I could just leave it as 36 and 6. All right, so what that tells us is that the 12 volts from the battery splits equally, and we've got 6 volts across each of these halves of the circuit. So if I go back up to my second circuit, so C4, C2, and C35, those all have 6 volts across them. So I can find the charge on them. Let me just move this over a little bit. So Q, the charge on 2 is just going to be C2 times V. So it's going to be C2 is, let's see, what was C2? 2 microfarads times 6 volts. That's going to give me 12 microcoulombs. And Q35 is going to be C35 times V. And those are all 2. So we've got 12 microcoulombs on each of these ones, because each of them is the same capacitance. Let's see, why isn't this drawing anymore? Switch to a different pen. Okay. It's going to be C4 times V, which is going to be 2 times 6, or 12 microcoulombs again. And if you look, 12 plus 12 is 36. And so we've got 36 microcoulombs total, just like we thought there should be. And I can do the same thing for the bottom half. Q1 is going to be C1 times V. Q2 is going to be Q6 is going to be C6 times V. The V is 6 volts again, and C1 and C6 are both 3. So now I've got 3 times 6 and 3 times 6, which is going to be 18 microcoulombs for both of them. And 18 plus 18, what is that up to? It adds up to 36. All right, so we had said earlier that there should be 36 microcoulombs across both of these parallel combinations, and we're right. Okay, so the last thing we have to do is just find what's the individual voltages and charges on C3 and C5. So I know now that I've got 6 volts from top to bottom, and that I've got on that combination C3-5, I've got 12 microcoulombs. So these are in series, so each of them is going to have 12 microcoulombs. So Q3 is equal to Q5, which is equal to 12 microcoulombs. What about the charges? What about the voltages? Voltage is equal to Q over C. So V3 is going to be Q3 over C3. 12 over C3 is 4. So I'm going to get 3 volts. And V5 is going to be Q5 over C5. So 12 over 4, which is 3 volts. Okay, so I can work my way back and figure out the voltage and the capacitance on each item in the circuit. So on a test, I wouldn't ask you to do as complicated a one, but you might have one where you have 2 or 3 capacitors and you would have to do something like this. Okay, so what's your assignment for today? Your assignment is for this relatively simple one where you've only got 3 capacitors. What's the equivalent capacitance? And then what's the charge on each of those 3 capacitors?